Okay, so today's lecture is on multilingual question answering, and this is the first time this lecture has been given, so please stop me anytime if you have any questions throughout this lecture. And so question answering is a topic that has been really popular in the last few years, so it really needs no motivation. But for the last 50, 60 years, there's been a futuristic vision of humans asking computers questions. And here's an example from a fictional movie where humans try to ask computers, like, what's the meaning of life? And while we're not there yet, we are at a point today where people actually use question answering day to day. I'm guessing most of you have used one or are using it regularly as part of your daily life. So for some examples of QA systems or tasks that you might actually be familiar with, the first is Lunar. This one you might actually not know, but it was one of the first QA systems to actually be used. It was developed by NASA to answer questions about the moon. In 2010, IBM Watson, or around that time, IBM Watson, which was co-developed by Eric Neubig at CMU, was introduced. And this was like the first QA system to really achieve human level performance on some domain. And it beat some of the best Jeopardy contestants in the world. And then in 2016, the Squad dataset was released. And this really spurred a huge amount of research into neural network methods for question answering. So do you notice anything in common with all these different systems that I just described? They're all in English. And this is really what we're going to talk about today, is how can we take these advances that have really been tremendous and apply them to languages that are not English. So just, I'm curious, can you raise your hand if you've actually tried to use a digital assistant to answer a question in a language other than English or about a topic other than English, like in the data? It's actually a lot of people. And so in the purple, how well did it work? Okay. Okay, so it sounds like there's an issue with the speech side of it and also with the question answering retrieval part of it. And so this is a paper that was just recently released by Graham and collaborators, where they tried to index different NLP tasks based on two axes. One is the number of speakers, like how much demand there is for the technology. And then the y-axis is the quality of the technology in that language. And you see the QA has like a huge drop off. After maybe the 7th or 8th most popular language, you see like a dramatic drop in performance. And this is actually a lot worse than most NLP technologies. Like something like parsing, it's actually a much smoother curve. And so I think this is important because to me, question answering is really about making information more easily accessible to people. And when you can't access information in other languages, you're restricting information access for a large portion of the world. So there's two kinds of QA that we'll talk about in this lecture. The first is open retrieval QA or open domain QA, which is where you have a question like, where did Beyonce grow up? And you have a corpus like Wikipedia that is presumed to contain the answer. And you search your question against the corpus, get a document that might contain the answer, and then extract an answer from that document. Houston being the answer here. The next kind is knowledge graph question answering. Here, you don't assume that your answer is in a corpus, but rather you have a knowledge graph that might be constructed by humans, or it might be automatically generated using information extraction. And here you convert your question into a graph query against the knowledge graph, and then get the answer that way. Knowledge graph question answering is especially useful in situations where you have structured data or you're querying against some kind of automatically generated data. So in this example, what will tomorrow's high temperature be? It's very unlikely that any corpus will actually have the answer to that question. And so On the other hand, a knowledge graph could be automatically generated using government data every day. And then that's where this can really be super valuable. So before I jump into Open-Retrieval QA, are there any questions about the task as we defined it? Okay, so we'll focus on Open-Retrieval QA, which in the multilingual setting has seen a really large amount of activity in the last few years. And then we'll spend only about 10 minutes at the end talking about knowledge graph QA. So for Open-Retrieval QA, just drilling into this example, we first want to extract a document here from Wikipedia that is likely to contain the answer. And this task, this subtask, is known as passage retrieval. And then after passage retrieval, you now have a document that is likely to contain the answer to your question. And then the next step is called reading comprehension, which is, given this evidence, what is the actual succinct answer? Passage retrieval is a standard search engines or information retrieval problem where you're given a query and a set of documents, and you want to retrieve the most relevant document D for the query. And when you frame it like this, the question is, how do you define this score function that scores a document given a question? And there's been a lot of work on how to define the score in some kind of optimal way. The most traditional approach, which I'm guessing a lot of you are already familiar with, is called TF-IDF. And here, effectively, what the motivation is that you want to choose documents that contain a lot of the terms in your query. But you might notice that not all the terms in the query are equally valuable. So in where did Beyonce grow up, did or where are very common words, but they're going to occur in a lot of documents. So the IDF term, the denominator here, discounts terms that occur in a lot of documents. And so ultimately, you're basically trying to find documents that contain a lot of terms that don't occur in every document. And TF-IDF was introduced about 50 years ago, and it's still very popular. But in the last 20 years, there was a modification that's become pretty much the standard baseline in passage retrieval, and this is called BM25. It's actually really conceptually the same thing as TF-IDF. You have an IDF term in the left. You have the document frequency being effectively discounting the importance of that term. And on the right side, you have your term weight. But the way that it really differs is that based on this observation that by TF-IDF, it really values documents that are long, because long documents are more likely to have term matches for any query. And so here you divide the document length by the average document length and use this to discount the term weight. So if you have a document that's much longer than average, then you better have a much greater term weight in order to recommend this document. And with BM25, you have two hyperparameters, K and B, where K controls how much weight you give TF versus IDF, and B controls how much you care about the document length normalization. And so these are typically tuned against some kind of validation set for your language. And one important note about BM25 that is really relevant to this class is that it doesn't require learning any statistical model. It's effectively just a heuristic that you can run against your language. And so this means that you don't need any data. You can run it against English or against Tamil or whatever language you care about. And just to highlight how amazingly well BM25 performs, you might have heard about OpenAI embeddings, which is this like flashy new API from OpenAI that promises to be able to encode any kind of data or text and do like really effective search. BM25 was listed as their baseline, and they didn't really talk about this too much in the paper, but it's surprising that their baseline model, like the small model, is actually worse than BM25 on most of the metrics, even though it was trained with self-supervision on a huge unsupervised data set. And BM25 requires very simple indexing, probably costs a couple of dollars, whereas the OpenAI model, which is actually worse than BM25, would cost around $20,000 to index a few million articles. And so BM25 is like a really great tool, and even for compared to the state of the art, it can be effective. I believe it was, actually, I don't remember off the top of my head. But, higher is better. I'm comparing BM25, which is the top row, with the smallest version of the OpenAI API. And on 3 of the 4 metrics, the OpenAI system performs worse. When you get to a much larger self-supervised model, it performs better. But. No, it absolutely is a problem. And that is a good point. In that if you have a language that maybe is very morphologically rich, then your token overlaps are going to really depend on how well you tokenize or how well you break up the morphemes in that language. That's a really good point. The tokenization is orthogonal to the BM25 algorithm, but BM25 is going to be very sensitive to how well you tokenize that language. Okay, so one problem with TF-IDF is that it will only recommend documents that contain a lot of the terms in the query. And so let's look at this example again. Where did Beyonce grow up? This document, which we know to contain the answer, it does contain the word Beyonce, but it doesn't contain grow up. It rather contains raise, which we know to be like the same, but there's a vocabulary mismatch problem here. And in order to solve this, we can use your standard pre-trained language models. And there was a paper a couple of years ago called dense passage retrieval that's become the standard baseline for passage retrieval using neural networks. And in this method, you encode the query and the document into vectors using the CLS token. And then you can just score the match between the query and the document as the dot product of these 2 vectors. So it's very simple conceptually. And you might be wondering how this is practical, because running BERT against a huge corpus, like all of your documents in Wikipedia, is really expensive. And it might take hours or days. And so how can you do this every time you want to search one query? The reason the DPR is so effective is that you can index your search corpus using BERT offline. Do it every night or just do it once. And then you have these vectors that are static. Then when you get a new query in your search engine, you can just encode the query using BERT. And it's just 1 sentence, so it can be hopefully quite fast. And then you can now just compare that query vector against your offline document vectors. And this comparison, which is known as maximum inner product search, there's algorithms to do it really efficiently. So the major downside with dense passage retrieval is that if you take these BERT encoders as just pre-trained from the original BERT without any fine-tuning, it often won't work very well. In order for it to work really effectively, you want to train it or fine-tune it on a set of questions that have each been tagged with a set of known documents that are known to be relevant or non-relevant to the query. And then you use this to fine-tune your encodings. And for this to work well, you actually need quite a large data set, which does not exist in most of the world's languages. So this motivates, but despite this, just to illustrate how popular DPR is today, here is the Papers with Code leaderboard for natural questions, which is a really popular QA data set right now. And the top 6 methods for passage retrieval on this data set all use some variant of DPR. And then the 7th one uses BM25, but it's quite a bit worse here. So before we move on to reading comprehension, are there any questions about passage retrieval? Okay, so now once you've retrieved a passage that is likely to contain the answer, the next task is how to extract a single answer from that passage. And this is known as reading comprehension. Now, sometimes, given this question, who is Beyonce's sister? this question cannot be answered by this passage. And in that situation, you have to tell the user as such. So now, having framed this question, there's two kinds of reading comprehension that we will cover in this lecture. The first is extractive question answering, where you assume that the answer is contained as a segment of the passage. In this example, Houston being a subset of the passage. And then the next kind is a more challenging setting where the answer is freely generated using the passage as evidence. And so in this example, which is actually a harder question than before, is Beyonce from the Southern United States? We know that Houston, Texas is in the Southern United States. And the answer is yes, she is from the Southern United States, but yes is not contained in this passage. So these are two problem settings that we'll talk about. We'll first establish a baseline for each. So for extractive QA, there's an approach using BERT that's become quite popular, and it's really simple, but it seems to do the job most of the time. And in this approach, so just to refresh, you have a question and you have a passage that has already been retrieved. And you just concatenate those two together, pass it into BERT, and then encode each token in your passage using BERT. And the key here is that because it's a contextual encoder, each token in the passage has been able to self-attend to the question as well. So you kind of have a question-aware representation of each token. Now, at each token in that passage, you can take that encoding, that vector, and then pass it through a simple linear classifier that predicts how likely it is that this token is the start or end of the answer. And it's important to note that one downside of this method is that you assume that you can predict the start and the end of the answer independently, which doesn't actually make a lot of sense. Like, really, there's some expectations you have that the start would definitely be before the end index, or the end will be relatively close. It's not going to be 1,000 characters away. But somehow models just tend to learn this behavior most of the time, and it's not too much of a problem. And then when it comes time to make a prediction, you just choose the index that has the maximum probability of being the start, the one that has the maximum probability of being the end, and then what's in between is the correct answer span. Any questions? That previous method assumes the answer is a span in your passage, but what if you want to do free-form answer generation? And in this setting, another very simple related baseline is to, again, concatenate the question in the passage, and then use a sequence-to-sequence model, like T5 being a very popular pre-trained one. Here you encode your question and passage together to get like a representation of them jointly. And then you use this to pass to a decoder that then generates an answer token by token. And so this is like a classic encoder-decoder model. And so this way you're directly generating an answer using a pre-trained model. So returning to the goal of this class, which is multilinguality, most data sets in Open Retrieval QA are only in English. So here is the papers with code, the set of most popular benchmarks for question answer on papers with code. And if you look at these 15 benchmarks, literally all of them are only in English. So there's two questions we're going to ask in the rest of this lecture. Firstly, can we support questions in a language where we may not have data? And then can we search against a corpus that may be different than the language that we're asking the question in? So this introduces two related problem settings, multilingual QA and cross-lingual QA. So in multilingual QA, your questions and your corpus that you're searching against and your answers are all in some language. But they may be in a language either that you don't have data for, or you want to leverage multilinguality in some way. So maybe you want to do Chinese question answering, but you only have access to an English language data set like Squad. And how can you do this? That's the first problem setting we'll talk about. And the second one, which is actually just a more general version, is what if you want to ask questions in one language, search against documents in another language, and maybe even return an answer in a third language? And this is called cross-lingual QA. Usually the questions and answers are in the same language because that's most practical use cases will be satisfied by that. So in this example, you have a question in Tamil, which is Beyonce Enga Valanda. And Beyonce is very popular in South India, but there may be less information about her on Wikipedia in that language than in English. And so here we want to search against English Wikipedia, get a document that contains the answer, and then return the answer to the user in Tamil. And this is called cross-lingual QA. So now we'll talk about 3 approaches to solving both these problems. And the first is zero-shot transfer, where you might remember in Patrick's lecture 3 lectures ago, he talked about different multilingual pre-trained models like MBERT, XLMR. These models have been taught basically what many different languages look like, what their statistics are and their properties in terms of the pre-training tasks, but they have not been taught to do question answering specifically. So the zero-shot transfer approach is to take one of these pre-trained multilingual models, fine-tune it against an English language QA dataset like Squad, and then hope that by learning to do English QA and based on its knowledge of what Tamil looks like, it can also learn to do Tamil QA without any explicit supervision. And so we saw in Patrick's lecture that these models tend to perform well in things like classification using this exact approach. So does the same apply to QA? And the answer is that it actually performs perhaps a lot better than you might imagine. So here, a model based on MBERT achieves like 45% exact match accuracy on a multilingual QA data set, which is actually perhaps serviceable for your application. But simply by adding just a few target language examples, like 4 or 10, you can achieve like 3 to 5% improvement, which suggests that there's actually a lot of room for improvement beyond this naive strategy. Parthik? That's right. It was fine-tuned on English QA data set. It means you take your multilingual model that's been fine-tuned on English QA, and then you just use that, and then give that a new language as input, and have it search potentially against documents from a new language as well. Right. You're never training it how to do Tamil QA.
It's pretty amazing that it works, actually, but it basically relies on the embedding space being similar enough that, you can play that a little bit.
So anything in this, the question, the paragraph and the answer is the same one.
In this data set, that's the assumption they make, but you don't have to make that assumption. In theory, this approach could actually support cross-lingual QA. The next approach, which is actually a lot older, this has been around since 2000s, and Taruko from LTI has been working on this for, she was working on this 15 years ago. This approach is to use translation. So imagine you have a question in a language like Tamil. A really obvious solution is just to translate that question into English, use an off-the-shelf English QA system, which we know works quite well, get the answer in English, and then translate it back into the language of your choice. So this is known as a translate test. And if you read the Reuter reading, which is one of the 3 readings for this class, he talked extensively about this method and its downsides. And there's a few issues with this method, even though it's really simple and actually quite simple to engineer. Firstly, you're relying heavily on an empty system to translate your question from, say, Tamil to English. And for a lot of low research languages, your MT systems are just not that good. And so you're going to see pretty serious error propagation here. And the second, more nefarious issue with this is that you're assuming that all your questions can be answered using knowledge in English. And this is like a very Anglo-centric view. And a lot of the practical use cases in native countries are not going to be able to satisfy this. And we'll talk more about the second point at the end of the lecture. I'll just skip this actually. And then the final approach we'll talk about is actually building off of the first approach of using a multilingual model, multilingual encoder. And this is a method for doing cross-lingual QA without doing any translation to bypass some of the issues that we saw in the first approach. And not only here do we want to do no translation required, but we also want to be able to search for answers and accumulate answers across multiple different languages corpora. So how can I combine Chinese, Japanese, and English Wikipedia together to get one right answer in your target language? And so in this is the architecture here. The first piece of this architecture is a multilingual variant of dense passage retrieval, which is the neural passage retrieval method that we discussed earlier. And this multilingual DPR simply uses a multilingual encoder to retrieve passages from queries of any language to passages from any language. Next, given a question here in Spanish, you can extract relevant passages from multiple languages. So here there's Spanish and Hebrew. And then now given these multilingual evidence passages, we want to now generate an answer in the target language, which here could be English. And in order to do this, they leverage another multilingual pre-trained model, which is a multilingual generator, MT5, that is conditioned on the evidence given and then generates an answer in the language of your choice. Yeah, I believe it can really be any architecture. I don't remember specifically the one they used off the top of my head, but any of those should be able to support this.
Would it work for generated QA?
Yes, it would. This is the part of this architecture that generates the answer is not assuming anything about where in the passage the answer is contained. Now, this is like a really nice, clever approach when you look at it. But if you just tried this using off-the-shelf multilingual encoders and generators, it wouldn't work. And that's because you actually do need training data to make these things work. And this is actually super challenging because while there are data sets for multilingual passage retrieval, there's almost no data that can support generating an answer from evidence from different languages. That's a task that doesn't really have any data set right now. And in theory, that would be like a huge issue for this. But they propose a solution that somehow works, which is iterative self-training. They start with a version of the DPR model that is not trained, not fine-tuned, and then they, given a bunch of questions for which you may not know the answer, you extract passages from Wikipedia, and then choose the ones that are likely to be correct using the generator, and then consider those to be like pseudo answers. So you're effectively running your model to get like pseudo answers, adding to your training set, retraining your model. And you do this multiple times until you reach sufficient performance.
And, we had a question about like what model they use here. So I looked it up and they used multilingual BERT. They said they tried XLMR and it didn't improve results. And this is actually, it's kind of interesting because it also matches a general trend that I've found. Like if you're trying to use MBERT or XLMR, you probably want to know which one you want to use. And it seems that MBERT is better at like content-based modeling. So like if it's on modeling entities or modeling other things like this, it seems that MBERT is better often, whereas XLMR is better at things like identifying word types or something like this. So like XLMR seems to be better at like part of speech tagging, dependency parsing, kind of like reading and identifying span space question answering. So for something like looking up the content within DPR, it makes sense to me that MBERT, based on my previous experience, it makes sense that MBERT is better. Of course, there's a whole lot of other models too, but I think it's worth remembering that some models are better at some things, other models are better at other things.
Like the retraining model, but is it fine-tuned for like sentence encoding like XLMR on top of the sentence transformer usually is like what we use for the sentence or like the whether the MBERT model is fine-tuned for sentence retrieval or is it the base?
Yeah, it's fine-tuned, right? Yeah,
It's
through the whole thing.
Yeah, in the beginning, I believe it's not fine-tuned for any kind of sentence decoding task, and then it's iteratively fine-tuned. Okay, so before we jump into how effective this method is, we need to define a few metrics. And by the way, there's a class at CMU on question answering. So if you really are interested in the nitty-gritty here, take that class with Eric Neubig and Taruko. But the three metrics they use, which are all pretty popular. The first is F1 score, where given a generated answer and then an actual answer, you can compute the precision and recall of the token overlap, and then compute the F1 score like that. Exact match is the generated answer exactly the same as the true answer, which here it's not. And then blue score has been defined in the previous lecture, so I'm not going to go into that, but it's effectively just n-gram overlap. And on XOR QA, which is a cross-lingual QA dataset, they post quite strong performance here. And I believe like the human level is around 70%. And the fifth method here is exactly what we call translate test earlier. And so you can see how much better a neural method that's been fine-tuned can be than this naive translation-based approach. Mm-hmm. Like they're using monolingual data. That's an interesting point. So he mentions that in the iterative self-training, they assume access to Wikipedia, which they use to help refine the pseudo answer. And is the access to that information kind of cheating against these other systems that don't assume access to that kind of external knowledge? I think you can make an argument for that. But if you just view this as trying to solve the problem as effectively as possible, it maybe doesn't matter. And I want to highlight here that the state of the art on a very similar English data set, natural question, which is actually collected in almost the exact same way, is 80%. And so even though this is effective and state of the art for this task, it's still a lot worse than English. So there's a lot of room for improvement here. The Quora model, yeah, it's the model, it's the approach to the
if there is no answer in the passage, you will not want to open an answer. So is there any study that compares the extractive versus simulated models and how overconfident they are? And oftentimes I've seen like all the outputs in
I'm not familiar with any, but I think that's a good question.
Yeah. So within the English, we actually have a paper, How Can We Know When Language Models Know? And basically what the paper does is it measures the calibration of like generative or extract like language models that read and then generate the output. And the answer is the models aren't super good, but in calibration, calibration means like when they say there's a 50% probability of the answer being correct, is there actually a 50% probability of the answer being correct? And if they are basically right about the probability of it being correct. You could just choose what level of confidence you need before you output the answer. And the models aren't necessarily extremely good at it out of the box. Like they can be like way overconfident or something like this, but you can also adjust them relatively easily to be well calibrated. And if they are well calibrated, that works. I'm pretty sure there's nothing on multilingual, so good class project maybe, I don't know. So it might be something to do.
I'm not sure about X squad, but I know that Tidy QA, which is one that I'll mention later, does have unanswerable questions. And so just, this is actually a great segue, Karthik's question, which is some data sets for multilingual QA. And so I'll just breeze through this, but there's these two data sets, which are both extremely popular. They do just machine reading comprehension, no retrieval. So you're given a passage and a question, and the answer is either contained or not contained in that passage. And they both, MLQA is larger, but they both are based on taking an English language QA data set and then translating it to the language of your choice. MKQA is an open retrieval QA data set based on natural questions, which is an English language QA data set. And they again translate all of the questions, answers, and corpora into the language of your choice. Tidy QA is, I think, one of the most impressive ones. Here, it's another very large data set, but here they collect questions naturally in each language. So they have users in, say, Tamil. Actually, I don't think Tamil is one of the languages, but in each language, they have users generate natural questions in that language, and then they search against the native Wikipedia for that language. And here they do have unanswerable questions. And the reason the Tidy QA, I think, is so important is that every other data set translated English QA pairs into a target language. And there's two really big issues with this. The first is that the translated questions, even using a human translator, may not actually be natural in your target language. So let's say you're translating an English question to Russian, which is like mostly a free word order language. It's very likely that your translator will actually use English word order because that was the source language. And that leads to like a version of Russian that's not actually that natural. And the second is that the answers are assumed to be Anglo-centric. You assume they can be found in English Wikipedia. And so here's an example of a question. Which Indian lawyer advocated the preservation of Marina Beach in Chennai? This question can be answered using Tamil Wikipedia. I checked actually, but it cannot be answered using English Wikipedia. So any kind of translation-based approach will simply not cover these kinds of questions. And then there's a version of Tidy QA that also supports cross-lingual QA by whenever you have an unanswerable question, looking it up in English if it exists, and that lets you test cross-lingual retrieval as well. And several of these benchmarks are included in the Extreme multilingual benchmark. So now I'll just spend a couple of minutes, we're almost out of time here, but talking about knowledge graph QA. And so in knowledge graph QA, the goal is to, given a question, to convert it into a query against the structured knowledge graph. And this query often takes the form of a like query language like Sparkle, which is like a version of SQL for graph querying. And this goal can be concisely called semantic parsing. Now, in terms of multilingual knowledge graph QA, very little work has been done in this space. I would say I've only seen papers in the last year or two working on this. And there's two known methods. Both are very related to what we've already talked about for open-retrieval QA. The first is zero-shot transfer, where you take a multilingual encoder, fine-tune it for English KGQA, and then try to transfer it to another language. And then the second method is translation-based adaptation. And in the paper by Zhu et al., they use this approach, but they make the observation that even if you don't have access to a good translator for your language, in knowledge graph QA, you may be able to get away with using much more word level or local translations. because in a knowledge graph or in the questions that query a knowledge graph, you don't need as much paragraph level, sentence level context. So here they use unsupervised bilingual lexicon induction to do word level translation of an English data set into a target language data set. And they find that this works actually pretty well. And so even though there hasn't been a lot of work done in knowledge graph QA, there have been a few data sets in the last couple of years. You can, the slides will be posted and you can look at these in your own time. But this creates an opportunity actually in knowledge graph QA where there hasn't been a lot of methods developed, but there are data sets that you can use. And so I think there's a lot of interesting questions that could be answered using this data that people haven't really thought about. And then some other interesting open problems that you can think about for your final project or for your future are in cross-lingual QA, we showed that there's a huge gap still between these state-of-the-art methods and either English language QA or human level performance in that language. And so this suggests that we're pretty far from having solved this problem in any kind of meaningful capacity. And now, one other point is that with multilingual QA, there's a lot of information that is actually non-linguistic that you can use to make the task easier. You can look at images in Wikipedia or fact tables, info boxes, and not much work has tried to do this. So I think that this is a really promising area for research. And lastly, building off of Alan's lecture on Tuesday, if you go to India and ask people to interface with a Hindi language QA system, they're very likely to ask questions in code mixed English. And I don't know much work that's tried to actually solve this. So these are all some open problems in multilingual QA. So for the discussion today, we had these three different readings. The first two were papers from conferences, and the third one was a kind of a summary blog post from an EMNLP tutorial. And the question is to think about a practical QA application in a language or domain of your choice. And given this application, think about at least two of these things, which are who would actually find this application to be useful? What methods do you think could actually work for this application? And if you're interested in kind of thinking like a researcher, what resources or strategies might you use to either improve performance in the system or evaluate how well it works? And any last questions before we go to discussion?
There means like a comparison of zero-shot transfer MT5 and
between MT5 and XLMR?
for zero-shot export. So you compare MT5 and XLMR. Is there a comparison MT5 and
Like, I don't know about the MT5 paper. I haven't read it very carefully, but it seems like that might be something they would have done directly in that paper. Just because like cross-lingual QA is a very common thing. It's included in all the benchmarks, like Extreme.
Yeah, and Extreme directly like is about zero-shot multilingual QA. So. You're asking how can you score different language passages from different languages? You can assume that I guess you can assume that your ranker can assign scores to different passages using some kind of language independent meaning representation. I think that would be the goal. But that's what it tries to do. Yeah, I think it actually works reasonably well.
So just one technical research topic for the spoken QA. I actually don't know so much about it.
I'm actually not too familiar with them.
It's a good question. There is. I think it was actually developed here by Alan. Yeah, by Sid and others. So I think that's actually the best way. I think they called it So yeah,
That was for, so I'm familiar with that data set. That was QA for, that involved translated or transcribed text. And so,
but because it's transcribed text, they must also have speech. Right?
oh, okay.
So yeah, I think there's that. I've worked a little bit on this, but I don't think there's a whole lot. I think in terms of multilingual spoken, I think there's a whole lot. But it'd be super useful, of course, because a lot of people